welcome back to Elevate Chem. I'm Jesse and this is another concept video. This episode is the first of 5 all about covering the concept of equilibrium. And to explore this concept, as always, we're going to be looking at a question because ultimately the best way to learn a concept is by learning how it's applied in an actual exam. So the first thing I want you to do is to download this practice paper. It's the VCE 2014 chemistry exam and it's question 6. I want you to pause the video now and have a crack at the question. Fantastic. Alright, let's get stuck into it. Hopefully as you went through the question, you found that there were some key concepts being addressed here, and I'm going to make sure that we really highlight those and don't just work through the question automatically. So let's have a look at this first question. Now when I'm reading this first question, I can see there's a bunch of numbers here, but right now I'm going to skip over that because I might not actually need them right now. So as we look here, it says, write the expression for the equilibrium constant for this reaction. Now we're not actually going to need any numbers here, so I can ignore that first little portion of the question. And instead, all I'm going to need is the actual equation. And of course, that's given right here. Now we all know what the equation for the equilibrium constant is. And it's always written as K, EQ is a little subscript, and it's equal to, in this case, the concentration of the products, which is hydrogen iodide, divided by the multiplied concentrations of both iodine and hydrogen. Now hopefully someone's yelling at me over the screen saying I've missed something, and of course I have. The products is actually to the power of 2, and the reason why is because we've got this coefficient out the front. Now guys, this is going to remain constant no matter what the equation is. It is always concentration of the products to their coefficient, in this case 2, divided by concentration of the reactants to their coefficient. It absolutely does not matter what those products or reactants are, aside from maybe a couple of you smart people sitting there thinking there is one exclusion. Yes, there is. But pretty much 99 times out of 100, this is what it will be. So all it comes to when applying this question, I have to see what the products are, and I have to see what the reactants are and work out if there's any coefficients I have to deal with, and then I just plug them in. Done. There's my 1 mark. Alright, so let's move on to the second part of this question. Determine the equilibrium concentrations of hydrogen and hydrogen iodide and calculate the value of the equilibrium constant. Okay, so it's now actually asking me to calculate KEQ. I have to work out what this is equal to, and we found before what that actual equation is. So there's 3 values I'm going to be having to work out here. The concentration of the hydrogen iodide, concentration of the iodine, and the concentration of the hydrogen. Keep in mind that these are the concentrations at equilibrium, guys. That's a really key bit here. I've been given some concentrations right off the bat, but notice that these aren't actually for equilibrium. We have been given one for equilibrium, and that is this 1.07 moles. So I'm jumping back into the question now because I know that I'm actually going to need some of those numbers. So let's write down right off the start that the concentration of the iodine at equilibrium is equal to 1.07, because I'm going to be needing that in a few seconds. Alright, fantastic. But how am I going to work out those other values? Now we know that equilibrium is all about the fact that reactions go backwards and forwards, and it's indicated by this little arrow here that's going backwards and forwards. And that means that there's this dynamic equilibrium, and whilst the forward reaction is occurring, there's also a back reaction. And it's really easy to work out what the actual concentration is at a certain time by using the fact that we had an initial amount and we have a final amount. And often students will draw up a table, and if you find that to be a really effective way of answering this question, that's fantastic. Personally, I don't use it, but I know it is a really foolproof method, so I'm going to write it down here for you guys. So we're going to have initial, then we're going to have react, and then we're going to have our final. And we're going to put our species just above here. So we have I2 plus H2 goes to 2HI. And of course, I'm just grabbing that from the question given up here. So what was our initial amount of iodine? Well, it's actually given to us right up here as 3 moles. So I'm just going to write that down. And then, of course, what we finished with is 1.07. And by final, we mean equilibrium here because we're talking about equilibrium values, and that was given right up there. Now for hydrogen, we're given the initial amount, That was 2 moles. But for the actual hydrogen iodide, we weren't given the actual concentration, the actual initial molar value, so we're not really sure what to start off with. In fact, this is all the information I currently have. But of course, we can work out what this value is right here, and how we're going to do that is we know that initial equals reacted plus final, or writing that slightly differently, react equals initial minus final. In this case, we find out that the amount of iodine that's actually been reacted is equal to 1.39, and that's just using some simple subtraction there. So great, we've worked out how much iodine has been reacted, but how are we going to work out those other values? Now we know that things react in a molar ratio. It's not 1 gram for this 1 gram, it's not 1 litre for this 1 litre, it's actually based on the number of moles. And thankfully we have this little ratio up here which tells us exactly what we're going to be doing. And if we look at it, it's a 1 to 1 to 2 ratio. And that means that if every 1 mole of iodine that reacts, there's 1 mole of hydrogen that reacts, or more specifically 1 mole of H2 gas. And there's also going to be 2 moles of the hydrogen iodide gas produced. So let's just use that. So there's 1-to-1 relationship between the I2 and the H2. So that means really simply, guys, that you write 1.93 here as well. That means because there was 1.93 moles of I2 reacting, and there's a 1-to-1 ratio, there's also 1.93 moles of H2 reacting. And now we wrote down that equation before, that initial equals react plus final. Again, if you plug in the numbers, you're going to find out that your equilibrium moles of H2 is 0.07. Now, some students might just sort of instinctively write down 1.93 here. Unfortunately, that isn't the case because of this coefficient of 2 out the front. That means I have to put in double the quantity. And if we multiply that 1.93 by 2, we get 3.86 moles. But what was our initial amount? Now, you could take a guess and assume that it's 0, but it's a good idea to actually read through the question and ensure that was the case. A mixture of hydrogen gas and iodine gas is injected into a vessel that is then sealed. So I don't hear any mention of the fact that there was any hydrogen iodide initially present, so I'm going to fill in a value of 0 there, and that means the final value for hydrogen iodide is 3.86 moles. I now have all of these concentrations, the concentration of iodine, concentration of H2, and the concentration of HI. And the reason why I actually have the concentrations here and not just the actual molar values is because I'm dealing with a 1 litre reaction vessel. Because of C equals N over V, where N is our moles, V is our volume, that actually means in this case that it is equal to N, as V equals 1 litre. So therefore, plugging all those numbers in, you get KEQ is equal to 3.86 squared divided by 1.07 times 0.07. And if you plug that into your calculator, guys, you're going to get the correct value of 2 times 10 to the 2. Alright guys, hopefully I'll see you in next episode, and we'll be cracking part 2 of our 5-part series on